Here's the free response from the summative assessment on gases. In question 1, we have a sample of oxygen gas pumped into a rigid cylinder with a movable piston. I want to calculate the density of the oxygen gas under the conditions given in units of grams per liter. The density is a measure of mass per volume. They do tell you that in the packet, or by seeing the unit gram per liter, that kind of gives me a hint to what I'm looking to calculate. Depending on what version you had, the volume was given, either 7.95 liters or 9.85 liters. So for density, we've got the volume, but we need to calculate the mass, which we could do using PervNert. I could set up PervNert, solve for moles, and then just turn moles of oxygen to grams of oxygen. So in both cases, we've got the pressure, we've got the volume. We're going to solve for moles. The pressure was given in torr, so we'll use the version of the gas constant R in torr. And then I've got temperature in Celsius, which needs to switch to Kelvin. All units need to match the units on the gas constant R. So we want liter, torr, mole, and Kelvin. But they do tell me in the packet that I can just add 273 to switch from Celsius to Kelvin. So once we get our moles, we'll just multiply by the mass of diatomic oxygen, 32 grams per mole. And then in each case, I should get a density of about 1.31 grams per liter. Part B, to change the density, a student proposes opening the valve on the side of the cylinder, pushing down on the piston to release some oxygen gas. Will this action change the density of the gas remaining in the cylinder, assuming that the temperature remains constant? Okay, so density is a ratio of mass per volume, but if I push down on the piston, I can change the volume, I can decrease the volume, but if I open the cylinder, I'm also going to release the gas. So both variables would decrease. I would have less mass of gas and the volume would be less. So that ratio wouldn't necessarily change. So we'd say no, the volume would decrease, but so would the mass. C, a second student attempting to change the density of the oxygen proposes cooling the cylinder to negative 55 degrees Celsius. Will this action change the density of the gas? So now I'm assuming that they're only going to change the temperature, but they're going to keep the cylinder closed. So we've got the same amount of gas. Now we'd say yes. At a lower temperature, the gas particles have less kinetic energy. They would start to condense, and so the volume would be less. The mass will stay the same, but the volume would decrease. And now, yes, that would change the ratio of mass to volume. And part D, what if the student further cools the cylinder to negative 180 degrees Celsius and observes that the measured volume of the oxygen is substantially lower than the volume that would have been calculated using the ideal gas law? What if they used PervNert to calculate like a predicted volume? And then they actually do this and they measure, whoa, the actual volume is way less. Assume all equipment is functioning properly. Explain why the measured volume of oxygen is smaller than calculated. Now they also kind of tell me that the boiling point, which is technically the point where we would switch from liquid to gas, is negative 183. Now depending on what direction the energy is flowing, I could also say then that the gas would condense at negative 183. I would go from gas to liquid. And so here we'd say when the gas is cooling, there's less kinetic energy. And now here we're significantly less kinetic energy at these really low temperatures. But now as the gas starts to cool and maybe condense, those intermolecular forces might be more significant. So if the particles are becoming a little more attracted to each other, because again, they're pretty close to that point where they would condense from gas to liquid, I would get a lower volume than I would expect. So something here about at this really cold temperature, the kinetic energy is so low that the particles will start to be close to their point of condensation, and intermolecular forces are going to start to become more significant. That's then why the volume is lower than what I calculated, because Pevnert assumes ideal conditions and ideal behavior, that intermolecular forces would not be significant. But at really low temperatures, they may. Question 2 has us comparing nitrogen and oxygen gases. In part A, I have a particle level representation of oxygen shown in the balloon on the left. The balloon on the right contains the same volume of nitrogen at the same temperature and pressure. In the balloon on the right, we want to draw a representation of nitrogen with the appropriate number and distribution of particles. So if the balloon is at the same temperature and pressure and volume, there must be the same number of particles. So we want to show nitrogen atoms, or I should say nitrogen molecules, diatomic nitrogen molecules in the gas phase, so still spread far apart, and there would be the same number of molecules, 4 molecules of nitrogen. Part B, the graph below shows the Maxwell-Boltzmann distribution for nitrogen. It's kind of like a fancy word for a bell curve that's showing the speeds of the particles in a sample of nitrogen. On the same graph, draw the distribution curve for oxygen at the same temperature. Okay, so the oxygen particles would be a little bit more massive, so they should be traveling a little slower. So just something that shows an average speed that's now slower than that of the nitrogen. Parts C and D. Dry air consists mostly of nitrogen and oxygen and a few other random gases, water vapor, all that good stuff, CO2. A student obtains a 500 milliliter container filled with a sample of air, dry air, at a total pressure of either 3.2 atmospheres or 2.3 atmospheres and 298 Kelvin. We want to calculate moles of gas in the container. No problem. We've got the pressure, we've got the volume, but it needs to be in liters. We'll solve for moles. We'll use the gas constant in atmospheres, and the temperature was given in Kelvin. So no problem. We can solve that for moles. Then in part D, the student cools the gas mixture until either the nitrogen or the oxygen condenses. Which will condense first? Justify your answer in terms of the types and relative strengths of intermolecular forces. All right, so here's a couple concepts that came back a few times. This idea of like intermolecular forces and how they may affect gas behavior. Because the oxygen's got a few extra electrons, the London dispersion forces should be a little bit stronger. More total electrons gives me like a more polarizable electron cloud. So if the London dispersion forces of oxygen are a little stronger than those of the nitrogen, I would expect oxygen to condense first. Then finally in part E, in the sample of air, it's about 78% nitrogen molecules and 21% oxygen molecules. Calculate the total number of grams of the substance that condenses first. So it's supposed to be the oxygen. However, if in part D you picked nitrogen, you would have lost the point from nitrogen. But if you did this calculation correctly, you would still get full credit. So I go back to my total moles that we calculated using Pevnert, and then they're saying that about 21% of the molecules are oxygen. So I multiply by that 0.21. It's kind of like a mole fraction, but We don't always have to multiply by a percent. They may have said like the mole fraction is 0.21, which is fine because that's usually how we would use it anyways. So then I should be able to get moles of oxygen in the air mixture, and we just turn moles back into grams.